charts. Part A says they want the probability of what?
Frequent and occasional people who are involved in charity work.
So frequent and occasional,
Yep.
or frequent or occasionally. Is that good enough? Can everybody understand that? So frequently or occasionally. So look at that chart there. How are we going to frequently or occasionally? So what's that telling us?
Total number frequently, and it's just the total of both.
All right, so for frequently, what's the, for frequently, how many people do it frequently?
428.
Out of how many?
2,850.
What are we gonna do here? What operation? We're gonna add, right? For occasionally, how many people?
886.
Out of the same 2850. Are these events mutually exclusive or not mutually exclusive? Can they both happen at the same time? So that means they're mutually exclusive, right? So do we have to subtract off anything? No, so all we gotta do is add those. Somebody help me out. I'll do the bottom for you. That's nice of me, Wayne. You guys take too long.
13. 14.
Here in a few minutes when we take this test.
Uh-huh.
Because Riley said that.
No.
Okay, well, he can.
Yeah.
Next one. A person is a female or not involved in charity work at all. So female or no charity. I'm guessing the bottom number is going to be 2850 again, right?
Yeah.
How many females?
1378.
1378 plus how many people not involved in charity at all?
1536.
Now, this time are these two events mutually exclusive?
No.
No, because now they could both, the females, right, not just the males are jerks and don't help people out, but some females are also jerks, right? So, how many females are there that don't get involved in charity at all? 731?
41.
Bottom number is gonna be 2850 again.
73.
2173. Now, please make sure, somebody add these two together for me.
2914.
So if you add 2914 over 2850, what's that telling you? There's something wrong. Because your probability has to be between 0 and 1, and we're more than 1 now. So that probably tells you that your events are not mutually exclusive, and you have to subtract off something. So if you come up with an answer like that, make sure that you go back and figure out why. Person is male or frequently involved. So male or frequently involved. What's our number for males?
1472.
That's out of 2850 again. How many people are frequently involved?
428.
Are these, we gonna have to subtract off anything this time?
Yeah.
Are there some males that are frequently involved?
Yep.
So how many of those?
220.
What's that come out to be? Now, all of these, could you change all of these to decimal form? Yeah, and it'd probably be better to change them all into decimals, because if I come up to Gage and I say, hey Gage, 1,314 people out of 2,850 people are frequently or occasionally involved in charity. That's not gonna mean anything to him. But if I change it to a decimal or a percentage and tell him that, that's gonna mean a little more. What is it?
46.1%.
About 46%. If I tell him, hey, about 46% do it frequently or occasionally, that makes a little more sense. Almost half the people do some kind of charity. Part D, person is female or not frequently involved.
Which is occasional.
Probability, female, not, what did it say?
Frequently.
Not frequently. So if it's not frequently, what's that saying?
Occasionally not.
So occasionally, not at all.
Yeah.
So we gotta do both of those, right? Sort of something there, and you can do this different ways, that's up to you how you do it. You could just get rid of part of it, you could add part of it, either way. What's our females? 1378 plus, how many people, let's just go ahead and do it now, how many people are occasionally or not at all? Add those two numbers together from the chart. 24, 22. Now we're gonna have to subtract off all the females that are in those two groups, right? So how many females are in occasionally or not at all? You're gonna have to add those two numbers together. Now I'm doing it this way and some of you are looking at me like I'm crazy. Was there other ways you could have done it?
1171.
Yeah. How much?
1171.
Thank you. Hopefully I didn't mess it up and we come up with something, answer that won't work. 26, 29? Is that all right? Yeah. It's a pretty high percentage, but. E, are the events being female and being frequently involved in charity work mutually exclusive?
No.
How come?
They can both occur.
All right, you can be female and frequently involved. They can both occur at the same time. Other questions? Is this stuff that easy? Sorta, and that's where you gotta be really careful, because if it says and, if I want them to be female and frequently involved, how many people am I picking this time?
How many people are
I'm just dealing with that one group. So I'd have to look at female and frequently involved. So if I look at that chart,
But for that chart, you wouldn't have to do any math.
that's 207, and that's out of the 2850. And that's just so you don't have to do any addition or subtraction. Does that make sense? And you got to be real careful, and I tried to make sure I explained this really, really well last time. I explain it, and you're looking at that one thing, or it's like you're doing this, and then putting them together. But they change a couple of words around in the sentence, and then everything goes out the window. Because it could be something completely different. Other questions? Ah!
I was gonna, I'm sorry.
Sorry, Sean. Riley made me do it. You did too!
I told you this is a good idea, but.
It wasn't good guy, I opened my eyes.
No, you went.
I did.
I thought you meant like drunk.
trying to listen to you before when you started.
Elizabeth probably jumped more than you did, but did you jump, Elizabeth?
It was just quiet for long enough for me not to.
No. Someone like, it's already like, not even second
And
grade.
Zoe, I wasn't watching Zoe, I don't know, she probably did
Already
too.
lost my phone.
I gotta get that.
Mike checked under the seats of a couple people that might have peed themselves.
Oh, yeah, I definitely did. My bad.
I'm gonna do the notes. My phone's working.
Additional topics for probability and counting. I was gonna do something else on this. Might do it here in a minute. We'll see at the end. Cause, I heard this morning on the radio that one of the lotteries is up to like 600 million or 700 million or something again. It's like the 6th largest one ever or something, I don't know. I don't never pay attention to them, but
Just buy it. Buy it.
we might look at the odds of actually winning, but I have to look it up how they do the numbers now, because they keep changing it on me.
That's a
That's
really
some
appreciate
guy
how it's
sorry.
Not this one, apparently, because this one they said nobody.
Whenever quadrillions it is.
All right, so what we're gonna do, determine the number of ways a group of objects can be arranged in order, determine the number of ways to choose several objects from a group without regard to order, and use counting principles to find probabilities. With this, all of these things that most of these things that we're gonna talk about with the counting principles and these two different things that we're gonna do, that's gonna give you your total possible outcomes. It's not gonna tell you a probability. It's gonna tell you how many total possible outcomes there are for any certain event. When we wanna find the probability, then we're gonna have to find the favorable outcomes and put that on top. Did I write something wrong? A permutation. Put that up there. Permutations and combinations, those are gonna be like two of the main things that we're gonna talk about today. This is another one where it's hard for me to explain this. Because I understand it in my head, but that doesn't mean that you're gonna understand it in your head when I say it. Permutations and combinations are really, really close to each other on what they are. So you really got to make sure that you understand the difference in them. So you know which one you're using, whether you're using a permutation or you're using a combination. Did we already use this symbol? I thought we used factorial earlier. Did we or did we not? No. All right, so factorial just means like this right here. If you got 6 factorial, just means 6 times 5 times 4 times 3 times 2 times 1. So it means you start at that number and you go all the way down to 1. On your calculators, I can't remember where it's at on your calculator. Let me grab a calculator and I'll tell you where it's at on your calculators. If you're trying to use a factorial button on your calculator, and you might want to have a calculator, and actually it does have a factorial button on it, but I'm going to show you this. Unless you want to move back there by Wade, or Wade move up there by you so that you can see your kind of calculator. Apparently Wade doesn't like you enough.
I know what it looks like on the calculator.
I know, but I'm saying so that you can see where it's at on your calculator. All right.
I have no idea where it is.
So on this, to find the factorial button, if you go to, let's see. Gotta find the button on mine. If you go to the math, there should be a math button somewhere on your calculator. Does everybody see it? My calculator battery's about dead, it's not working. You go to math, and then Once you're on math, you scroll over to the right where it says PRB. Even if you, because we're going to do other formulas, that you need to know this. So the math button, then PRB, scroll over to it. And the fourth one down on my calculator is that exclamation mark. So if I go back to my original screen and I put in 8, math, scroll over to PRB and go down to factorial and hit enter, it'll show up 8 factorial on my calculator. You hit enter and it tells you how many there is. All right? Now, where that would be used at, when we were talking about pizzas, when we first started this chapter, we were talking about pizzas and the different possible toppings that we could have. If we had 8 different toppings we could have on the pizza. If we pick one topping, we got 8 choices. But if we pick 2 toppings, we got 8 times what? 7. We pick 3 toppings, 8 times 7 times 6 for the third choice, right? Then times 5, then times 4, then times 3, then times 2, then times 1. What that tells us is all the possible outcomes for all the different pizzas that we could make if our pizza place had 8 different toppings. I think it was like 40,000 in some or something like that. 46,000. So that's factorial. 0 factorial. This is one of those oddities in math that we do because it has to fit into a pattern. All right? 0 factorial is always 1. If you go into higher level math, you'll see some of them where you'll see different things where there's a pattern in math, and there's one right in the middle there around 0 or something, and it's just a little funny, but it fits the pattern, and that's why it's that way. So 0 factorial is 1. There should be another slide here, and I'm trying to figure out why it's not here. There it is, all right, so look for that. The objective of a 9x9 Sudoku number puzzle is to fill the grid so that each row, each column, and each 3x3 grid contains the digits 1 to 9. How many different ways can the first row of a blank 9x9 Sudoku grid be filled? So this first row right here.
Slant.
Slant.
That was my guess.
Somebody went by, just knocked on it, didn't ring. They were beating up with it, so I saved the flies off. How many choices do we have for this first one right here? 9. Really? Is that right?
Yeah.
9? How many choices for the second one? Third one?
1.
What are we going to do with all those? Multiply them together, and that's where the 9 factorial comes in. So that first row, 362,880 different ways that the first row of the puzzle could be set up. So if we start to make this puzzle, 362,000 different ways that we could write the numbers into that first row. In factorial, I'm not sure, we just found, oh, I know why. I was going to show you on the calculator. Everybody found it on their calculator, right? Now, the other thing I want to put down here, math, PRB, all right? There was other things on there, 1, 2, 3, 4. The factorial was number 4 down here. These other ones here, we're going to use more than that, so know how to get to them, because that's what we're getting ready to go over right now. Maybe I shouldn't show any on the calculator. Maybe we should just do the formulas on all these. That'd be better, wouldn't it?
No.
Yeah, let's do the math. Write this down. On this formula for permutations, these two formulas today, one permutations, one combinations. With permutations. Again, to try to make it, this is the way I remember it. The difference between this and combinations when we get to them. A permutation I always think of as a race. When you have a race, does it matter which order the competitors finish in? Yeah, that's the whole purpose of having a race, right? To see who finishes 1, who finishes 2, who finishes 3. Anytime you're doing something like that, it's a permutation. All right? So if I have, how many people we got in here? 1, 2, 3, 4, 5, 6, 10, 14, 17, 18 people. So we got 18. Our N is 18 this time. There's 18 of us and we're going to race. And we want to find the probability, we want to find the different possible ways that the 18 of us can finish a race. All the different possible outcomes. This N stands for your total number. The R stands for how many you're taking at a time. So we're going to run this race, and usually when you run a race, what matters? The top 3. So that's the number we're going to use here is 3. So our permutations are going to look like this. P, 18 people taking 3 at a time. And we're going to figure out all the different ways that we could run the race. Now we know this isn't true because we sort of need to get rid of the number 1 spot because we all know who's going to finish there. What's N this time? N is 18, R is 3. Now Gage was throwing a fit, didn't want to do the math here, but watch how easy his math is. What's 18 minus 3? Now what happens here, give me just a second.
A big number.
That's all on top, right? On bottom. Is there really any reason to write all those out? When you look at this, what's going to happen with all of this and from 15 down that way? They're all going to cancel out. So all we really have is what? 18 times 17 times 16. That's going to be our answer.
4,896.
Yeah, it's pretty easy on the calculator, you go
Do you just type in the
18
numbers, you know?
factorial divided by
Yeah, in this case, so in this case, you could stop right there and on your calculator, type in 18 factorial divided by 15 factorial, and that's not too difficult either. But again, you gotta push the math button, the probability button, scroll down.
I just
put it
use
in
the
there.
B.
It's not that much work to get to here, so.
18.
You just did what?
I just use the P.
Oh, there's a P button on there?
You got a P button?
Sure, sounds great.
So, what they're talking about, go back to math, on your calculator, go back to math,
We got a P one.
go to PRB,
We do got CS.
Where's our P button?
I got in PR.
Goes P.
and you should see something that says this, NPR. Which one is it, the second one down?
Yeah.
Now, the bad thing with using the NPR button, you got to remember, and I forget to do it all the time, if we're doing this, what do we have to do before we go to math?
18.
You gotta type in 18 first. And I'll do it all the time, I'll push the math button and stuff and get in there and then think, oh crap, I forgot to put in the 18. Then you gotta go back, put in the 18, then go back to it all again. So you type in 18, go to that button, and it'll pop up on the screen, NPR, and then you type in 3. And what's it tell you? 4896. Those are the possible ways that out of our class here that we could finish a race, the first, second, and third place. All right? Now with combinations, what's different is this. If I take these 3 books, for permutations, I could put these 3 books this way, and that's different than if I put the books that way. Because if they're racing, this book wants to be ahead, right? So that's different than that. That's different. That's permutations. If we're dealing with combinations, and I take these 3 books and I'm picking 3 books to take with me, does it matter if I'm carrying them this way or this way? No. So combinations, the order that they're in doesn't make a difference. And when we get to that here in a second, that's how you need to be able to tell the difference in them. Permutations, again, I think of a race. Anything that's going to be like a race where it matters that Phoenix's name is first, then Gage's name is second. Anything that's that way is a permutation.
What's his last? Who's second from last?
Find the number of ways of forming 3-digit codes in which no digit is repeated. So we got a 3-digit code. How many choices are there for that first digit? What are our numbers that if we're doing
1 through 9.
1,
Or is it 0 through 9?
0 through 9 probably, right? On a
Master.
locker, or not a locker, but a lock like this, a padlock, be 0 through 9. So how many choices for the first one?
10.
10. If you can't repeat them, then how many choices for the second one? 8. If you could repeat them, how many choices for the second one? 10. 10. We did that earlier, it's just 10 times 10, that's 1,000, right? So this one is what, 720? Is that correct? So different ways, if no digit is repeated, that's how we could do it. 720. Now they did it using permutations. Using permutations, how many total numbers do we have? 10. How many are we taking at a time? 3. What did it come out to be? 720. Fundamental counting principle, we could use a lot of times instead of using permutations, depending on the problem, and that's what I did here, was use the fundamental counting principle. Different ways to do it. Notice, again, all that canceled out, and it's just 10 times 9 times 8. 43 race cars started the 2007 Daytona 500. How many ways can the cars finish first, second, and third? What's our first number? 43 out of, and how many are we taking at a time? 3.
74046.
74046. So 74,000 different ways that race could have been finished.
Earnhardt wins.
Earnhardt was dead at that point. Well, which Earnhardt?
Junior.
Oh, then he wasn't dead.
And the other Earnhardt. Can't make.
Again, what I just said, sometimes you can just use the fundamental counting principles. We talked about that at the start of this chapter. That's where the pizza comes into place. If you have 10 choices for the first topping, 9 for the second, 8 for the third, so on, so on, so on, you're just multiplying them together. That's sort of the same thing. So if we pick 3 students from our class, we said there's what, 17 of you? So how many could I pick for the first name? 17. How many for the second? 16, third. We could use that, or we could use this. 17 items taken 3 at a time. Somebody do each one of those for us, and let's see what we come up with.
First one's
40, 80.
But the second one's 4380.
Second one's 40, 80. Really? No, they come out the same. So either way, doing it either way, it's going to give you the same answer. Now again, if we're picking 3 students from the classroom, that's saying that we want the students' names to be in some kind of order. So maybe the first student I'm giving $10 to, second student I'm giving $5 to, and the third student I'm giving $1 to. 50 cents?
I'll take it.
Now, what if I said I was going to give $10 to every student that I picked? Would it matter which order you came in? And that's where combinations comes in.
First combination.
Distinguishable permutations. To find distinguishable permutations. Go ahead and probably want to write down at least the formula and stuff there, and then I'll talk about it. Give you a second. This is sort of, I don't want to say it's hard, but it confuses some people. Gage, you have relatives that live down like Dixie?
Yeah.
They drive, do they do demolition derby stuff?
Yeah.
What's his name?
That guy's a stud.
Pulled in to fill up gas the other day, and he was sitting in there and had Lesh written across his.
Did he have a red beard?
Yeah, probably, I don't know. I didn't really see him a whole lot, because I was.
Was he sitting in the corner?
He's
with
good.
everybody else
He
did
went
it?
inside while the woman was out there pumping the gas and doing everything.
Was he sitting in the corner waiting for everybody else to do everything?
That's sort of a signal. I didn't.
He does that in derbies too.
Does it? Yeah. He was inside and she was out there doing all the pumping the gas and everything, so I don't know. No, I don't know. But he was inside most of the time, and then she was out there doing so.
Is he our new teacher?
Yeah, this isn't a real good one, but we'll use it.
Is that our substitute?
It's just an easy name to write.
It's pretty much.
He's the teacher for the day.
distinguishable permutations. We want to use the letters here in Gage's name, but we want, and we're gonna make new words out of them, but we want them to be distinguishable. So in other words, is everybody watching? Did you see me switch the two E's?
Yeah.
You see it? It's not distinguishable from what it started out being, right? We want it to where if I change something, you actually know something was changed. So we want to know how many different ways there are to change things and actually see that things were changed around. So this would be a distinguishable permutation. To find those, this is the formula we use. How many total letters do we have? 8. So 8 factorial. And then what you do is you take each one of them and you decide how many of them that you have of that certain item or that certain letter in this case. So how many G's do we have? So we just use 1 factorial. How many A's? 1 factorial. How many J's? 1 factorial. Do I really need to write all these 1 factorials down? No, because that's just 1 and it's not going to change anything. So the only one that we really need to deal with here is what? The E's. How many E's are there? So we do 2 factorial. And we do this, 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. You can cancel those out. And all you really got to do is multiply 8 times 7 times 6 times 5 times 4 times 3. And that'll tell you how many different ways we could, or how many different words we could make out of those letters. Now, are they going to be sensible words? No, that would take a whole lot more time and effort to do. So all you're doing is taking, let's just do this. How many total letters? 8 factorial again. How many E's?
3.
So 3 factorial. How many B's? 1. We really don't need that. We already got the E's. How many R's? S. We already got the E's. So this is just going to end up being 8 times 5 times, 8 times 7 times 6. I don't know where I got 5 from. Times 5 times 4 times, do we need the 3? So we just multiply those together. That'll tell us how many different words we can make out of the letters in Ebersole. Now, if we don't care if they're distinguishable or not, then we just use the P, 8. How many letters are we going to take at a time? All 8 of them, right? Punch that into your calculator real quick. 8P8. Four zero 312 320. So 40,320. Now let's do this. We're getting ready to get to this formula for combinations. We take all those letters and we're taking them 8 at a time, and we want the combinations where the order of them really doesn't make any difference. We're just taking all the letters. 1. Because how many ways can we have these 8 letters here, and if we take all 8 of them, how many different ways can we take them? Just 1. We're taking all 8 of them. So if we took this, find the permutations, how many letters are there? 7, so it'd be 7 taken 7 at a time. If we do the distinguishable, it's 7 factorial on top. How many A's are there? 4 factorial times, how many B's? 2 factorial, and C's are just 1. Somebody do this one, and I'll do this bottom one here real quick. So this is 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1 times 2 times 1. I'm going to cancel this out, cancel that out. Then I just do 7. Here I'm going to do a little math here. 6 divided by 2 is 3, so I'm going to change that to 3 and get rid of those. 7 times 3 is 21. 21 times 5 is 105. If I get 7P7, 5040. So 5,000 different permutations compared to, if we want it to be different, every one of them look different, there's only 105 of them. What's the probability that I pick that if we want them, if we don't care if they're different or not? How many of them come out that way? What's the probability if we want them to be different? 1 out of 105. Put the rags back up here. Because it's doing PIMDOS, so it's doing division, then it's taking that answer and multiplying by that. So to do that, you need to put parentheses around that bottom part. A building contractor is planning to develop a subdivision that consists of 6 one-story houses, 4 two-story houses, 2 split-level houses. And how many distinguishable ways can these houses be arranged? Just love it when these contractors, you go to some of these places and you can tell they didn't put a whole lot of thought into it, because you got a house right here, then a house right here, and they look exactly the same. That would drive me nuts. I don't know why anybody would buy a house that looks exactly like their neighbors, but some of them though, you look at them and they got a house here, then this one looks different, and then on down the road there's another house that looks like the first one. That's not too bad, but to put them all right next to each other. So on this, if we want all the distinguishable ways, so we don't want, just because we put a 1-story here and then we put some different 1-story here, that's the same thing. So to do that, how many total houses do we have here? 12. 12 houses, so it'd be 12 factorial over 6 factorial times 4 factorial times 2 factorial. And if you wanted to do all that, hoping I have the answer here, of course not. Yes. 13,860. Distinguishable. Now, if we didn't care if 1-stories were all right next to each other, are there going to be more ways or less ways that they could build this? More. But if we do care, which they should, because I'm sure it makes it harder to sell. How many different 4-letter words can be made from the word statistic? So 4-letter words can be made from that. If we were doing permutations, how many letters are in statistic? 10? How many letters are we taking at a time? Now the bad thing is, if we take a 4-letter word, and let's say we take S-T-A-T, is there other ways that we could end up with S-T-A-T? Yeah, because we got these other S's in there. So if we want them to be distinguishable, then it's going to have to be 10 factorial over, how many S's are there? 3 factorial times, how many T's? 3 factorial times, how many A's? 1. How many I's? 2. S's we already did, T's we already did, I's we already did, C's how many? S's we already did, right? So that's all of them.
50,000.
How many?
50,400.
different four-letter words that we could make. Is that right?
Yeah. It's just 10P4 would be 50/40, so it's like you just multiply by 10.
This would be 50/40? Maybe we did something wrong there. What did we do wrong? What did we do wrong here? Do I see it? How many letters are we taking at a time? So what should be on top there? Is that gonna work? That's not gonna work, is it?
Hit .33.
Yeah, that's not gonna work. So how could we figure that? Four-letter words. So we got 10 letters, we're taking 4 at a time. Huh?
Will an answer pop up?
I don't know. I'm trying to see if you guys will think a little bit here before we go on.
It's not four-letter word, is
These are, this would be right, except for it's gonna give us those ones that,
it? We don't.
that repeat, right? Like STAT would repeat. Oh, it doesn't tell us the answer.
We'll never know.
Never know. Anybody have any ideas?
4 is not the number we're supposed to be using.
It's a wild guess, but I agree.
You're sort of right. Go ahead and write this down. Maybe I'll tell you here at the end.
That could be like a trick question on the test.
Yeah, it might be.
Rat.
So combinations, selecting a selection of R objects from a group of N objects without regard to order. Again, if I go back to the books, it doesn't matter which order I stack these books in. I still got the same 3 books. That's a combination. So this combination of books is the same as that combination of books. But this permutation of books is different than that permutation of books. Alright, so for combination, is the combination number going to be bigger or smaller than a permutation? Smaller. Because we don't care when we're running our race, we don't care who finishes first, who finishes second, who finishes third. So those 3 people finishing in that order is the same as that finish. Alright? So that's what we're doing. We're sort of getting rid of all those ones where they're all the same. When you're doing a combination, I like to think of something like a committee. If I'm picking people for a committee, does it matter which order I pick them in? No. So if we're picking a committee to go talk to Mr. Harrison about letting Mr. Ebersole retire early. We need a committee like that. If we're picking that committee, it doesn't matter which order we pick, you get picked in, as long as you're picked. All right? And that's where this extra part of the formula comes from. Again, on your calculator, if you go to math, probability, and then what is, I think it's like the third one down, isn't it? It's got NCR. Again, what you're gonna have to make sure you do, you gotta make sure before you go to this button, you put in the N first, the total number that you're dealing with. A state's Department of Transportation plans to develop a new section of interstate highway and receive 16 bids for the project. The state plans to hire 4 of the bidding companies. How many different combinations of 4 companies can be selected for the 16 from the 16 bidding companies? So Brendan's company, do they care if they get picked first or fourth? No, all they just want to be picked so they get some of the state's money, right? So when we do this, that shows you that it's combinations. What's the number that's going to be out front? 16. What on the back side?
1820.
1820. So 1,820, is that what you said? Now, might it make a difference? Yeah, if they put the problem in there and said, the first company that we pick, we're gonna give this great big huge job to that gets more money, earns more money than the second job, third job, then it might be permutations. But for this one, the way they said it, combinations. A student advisory board consists of 17 members. 3 members serve as the board's chair, secretary, and webmaster. Each member is equally likely to serve any of the positions. What's the probability of selecting at random 3 members to hold those positions? So if I pick Riley, Gage, and Brendan here, what's the, out of the 17 of you, what's the probability that I pick those 3? Does it matter which order I pick those 3 in? No. So when we do this, we find the combinations. They found permutations, why was that? Did it say it mattered?
Yeah,
Yeah,
so
so
that everybody
it's-
has an equal chance or something.
Yeah, but does it? It wasn't like
said-
president, vice
yeah.
president, oh, was
It
it
was-
president?
it was
board
chair
and
board or
secretary
like-
and,
So I guess maybe one of those is more important than the other. So if one of them's more important than the other, then Riley wants to be the more important one, right?
Sure.
So then it would be a permutation. I should have read the problem more carefully. If that's our number, that's our total outcomes, what's the probability gonna be? I pick those. 1 out of that, which is about
Very high.
0.02%. Not a very good chance.
You might guess
Whether the arrangement spells the word Mississippi. What's the probability that we have all these letters in a hat somewhere and we're picking them out and it's gonna spell out that word? It's gonna be a lot, you think? How would we find it? How many letters are there? 11? So 11 letters, and we're taking all 11 at a time, right? So is that gonna be a permutation or a combination? Permutation, because we want the order to be that certain order, right?
Yeah, Sean. 39,916,000.
So now we dealt with what here? Distinguishable permutations, right? Because just because we change this I and this I, is that gonna matter? No, so
Yeah,
one,
the other number's bigger.
so it'd be this number 30, the other number's huge, isn't it?
Yeah, it's 39 million.
So one out of that, 34,650, about 2 1,000ths of a percent chance.
Good eye.
Yeah, very good.
I definitely like the other ones.
Oh, why are we skipping the corn one?
So now we go back.
Skipping the corn one on that?
Food manufacturer is analyzing a sample of 400 corn kernels for the presence of a toxin. In this sample, 3 kernels have dangerously high levels of the toxin. If 4 kernels are randomly selected from the sample, what is the probability exactly 1 kernel contains the dangerously high level of toxin?
Such a beautifully worded.
So how many of them contain the toxin? 3 out of the 400. So if we have those, do we care which one contains the toxin, which order we pick it in? No, if we're gonna die from poison, it doesn't really matter if it's the first piece or the third piece that kills us, right? So that really doesn't make any difference.
I wouldn't even hear that corn.
So there's 3, right, that'd be the best thing to do, right? So the possible, watch closely on this one, this is a little tougher, and this goes back to the other one. The possible number of ways of choosing 1 toxin kernel out of 3 toxin kernels, there's 3 different ways, right, that we could choose it. The possible number of choosing 3 non-toxic kernels from the 397 non-toxic kernels is 10,349,790.
A lot better.
So when we have that, that's going to tell us our total possible outcomes that we could get. We multiply them together. So because we could pick, we got 3 different ways to pick one with the toxin, 10 million different ways to pick one without a toxin. Well, if we multiply those together, that's going to give us the total possible ways to pick, that we pick anything. The number of possible ways of choosing 4 kernels is, we got 400 taken 4 at a time, so we got that. Then what we do is we put one over top of the other. So this is, what was this? This was different ways of picking one, or no, different ways of picking none over the total.
That's still too high of a percentage to eat toxins.
So about 3% chance that we're gonna
We're gonna die.
get one with the toxin in. You'd rather have 0?
You're not gonna tell us the answer, are you?
And we're gonna figure it out. Maybe I should make that part of the homework.
I won't do it.
Right. Write down all the 4-letter words that you can make from.
The actual.
I'll write down one.
Right now.
The
actual word.
What if I
No.
put it like on one?
Do what?
What if I just print it out?
What if I just don't?
what could we do here? We just sort of, a couple of those problems that we did there at the end sort of gave us some idea. Does the order make a difference? Are we using permutations or combinations?
Permutations.
How many letters?
In statistics or?
Yeah.
Oh,
10, and we're taking 4 at a time, right? Somebody figure that out for us again.
50, 40.
So there's 50,400 different ways that we could write.
40.
Oh, 50, 40, so 5,040. Different 4-letter words that we could make from that. But, do we want all of those?
We want the distinguishable ones.
We want just the distinguishable ones, right? So we really don't want this. How are we gonna figure out the distinguishable ones?
We're gonna put it
How many different letters are there?
No, I meant like, there's multiple, there's 10 total letters, but there's multiple acid, multiple disease, multiple
So there's 5 different letters.
So 5 different letters? So do we put that on top?
Sure.
Sounds great.
Yeah. Wait, so.
Sounds like a plan.
These are the different 4-letter words, correct?
Yeah.
5,040. Different 4-letter words. The bad thing is that we need to know how many of those are the same word over again so we can get rid of them, correct? How could we figure that out? Michael sort of had maybe.
Same amount of letters, like the same letters can't be in there.
So we want something where,
The S's and there's only one S.
so if we did that,
And there's only.
how many different letters do we have?
You have 2 eyes.
Sorry.
We need an S and we'll get rid of one more.
That's
So
what-
5.
That's what I meant to erase.
5.
There's 5 of them. They could be repeated. So what could we do there? So what are you gonna put?
5.
What's that give us?
So there are 120 possible.
That most would be like 120.
But those won't repeat once there's not.
So we won't have like a word that has like.
Double S.
Yeah, like an S in one spot and an S in another.
You can't switch them around. They're all different.
Those are 120.
So is that how many we have? How many different 4-letter words we could make? I heard, yeah, I heard that.
It seems too little.
Seems too little.
Seems good. I think that's good.
Because like you can't do the word stack.
Yeah. Go up.
S T A T.
Go with
Because
my
there's
gut.
The T, you only have one T there.
Oh, so that won't work, will it? Because even, so we got rid of those letters, but what happens?
Get rid of the snap word.
You get rid of
The
some of the
word.
words too, because we got 4 different spots that those letters could fall in. So do we really want to get rid of those letters?
Is this the thing where you gotta point like exclamation, how many S's there are exclamation points?
So that's gonna have to be part of it somewhere, isn't it? Distinguishable. So if we wanted, how many distinguishable 4-letter words are there?
Would it be 50, 40 divided by?
The non-distinguishable.
Would that work?
Sounds like it'll work.
So that, you're on the right track. So we got, how many total non-distinguishable 4-letter words?
50, 40.
50, 40. The bad thing is, if we do that distinguishable, we're using how many of the letters? We're using all of them. We don't wanna use all of them, do we? How many do we wanna use at a time? Just 4 of them. So what can we do? We tried this, but did it work?
You just
Put 10.
10 P4 on top? So that'd be the 50/40, right?
You do 10 minus 10.
10 minus 4?
Not like,
What do you mean?
I don't mean just 10 minus 4. Yeah.
Like that? I don't know, would that work?
Shot start.
Probabilities, statistics,
6.
you should tell us.
I don't wanna tell you, cause I think Gage is gonna go home and he's
I'm
he's
just gonna Google it.
he's
to
gonna,
be honest.
he's gonna sit and do this.
I will not do that.
And do all 5 40 of them, 40 of them?
And then he's gonna go back through and say, oh, no, that repeated.
How long, I wonder how long it would take Gage to do
The
it.
only word I can get out of it is
It's
cash.
long.
And staff, other than staff.
I'm not talking about real words now. If they ask you for real words, does that throw in a completely another
That
problem?
throws in something else.
Yeah, that, then you probably actually have to write them out and see which words
Are real and which
are
ones aren't.
real and which ones aren't.
You should just tell us the number for this figure. So is this gonna be our cliffhanger? We're not gonna know?
I'll tell you next time.
And so we come back, he's gonna forget, and then we'll forget.
We're never gonna know.
Oh,
Well,
well, that's fine.
Come on now. You think Maddie's gonna forget?
Yeah.
Possibly, yeah.
Sure.
She's human too.
That's true. Sean will remember just to,
Sean,
cause he likes to be annoying sometimes.
Yeah, say you
He'll
remember.
remember.
remember how we were playing with my calculator last month?
Yeah.
Yeah, I can't do log bases.
Oh, I know. I saw it's in the math button.
I'm just stupid.
I'm like, these can do log base.
Exactly, I was sitting here like, wait a minute.
I was gonna tell Larkin.
It's under math.
Yeah, it's
Log bases, because this calculator, when you just do the normal quick log, it automatically bases 10.
You can change it.
You can change it?
Yes, you can change the base.
And Larkin was saying how the TI Inspire, there's a button to change it.
Yeah, I got the big fancy one. I just don't remember. I don't care if I don't know. I'm trying to get it in a snack.
Right, I don't know how to cook the advertisement for you. My email just to Grant.
7 different words a day. What did you want?
I was saying do the like 540 and then like.
Just
how
telling
to
me
distinguish
50,000 more.
between
Hey, Gage.
I was like, oh, it's supposed to just pay.
10 or 4
You're waiting for us.